invitation, and I have the pleasure to now give you a short overview on the research we are doing, which is mostly related to heating and cooling with geothermal energy. And you might have seen temperature stripes before, which usually indicate climate change in the atmosphere. So each stripe is 1 year. Dark blue are cold temperatures, dark red are warm temperatures. Although this is not atmosphere, this is from a drinking water well in close to the city of Karlsruhe. So it shows that climate change is not only affecting atmospheric temperatures, but also the subsurface. And at the same time, this indicates that we can use the subsurface for heating and cooling, especially for heating because temperatures are going up. So, some echo.
Sorry, we've got an issue with people online and being able to hear.
Oh, the online,
Okay,
some people are struggling to hear, but echo is gone, I think.
the echo is going again. Okay, good. Yeah, so I'm not going to talk in detail about climate change and the need for energy transition from fossil fuel-based to clean energy. We have a couple of options to do this. Yeah, from battery storage to wind farms, solar energy, and so on. And that one very important pillar for reducing our carbon emissions is geothermal energy, especially for heating and cooling, because, well, in Germany, and I guess in most countries worldwide, heating and cooling is one of the largest sources of CO2 emissions. There's deep geothermal as well, of course, which I'm not going to cover in this talk today. To distinguish a bit or to look on where the energy is actually coming from, if you're looking for deep geothermal energy, so yeah, the limit of distinguishing here is at around 500 meters, which depends on really which report or website you look onto. But yeah, deep geothermal energy really comes from the inner of the Earth, from the kind of leftover energy from the formation of the planet Earth. If you're looking to shallow geothermal energy, it's more ground source energy. So it's actually more related to solar energy and the absorption of heat at the surface. Or if we have, like indicated here with the cold meteoric waters coming from rainfall, we can also use the sort of heated groundwater to harvest our energy, basically. And yeah, we can do this by different systems. So I have here that kind of schematic view of different systems. On the left-hand side, you see the deep and high temperature systems, which sort of always are based on very specific geological settings. So for enhanced geothermal systems, you need a very deep boreholes. You need some fractures down here, or if you don't have them, you might want to create them yourself, which then has the risk of induced seismicity, or you can go hydrothermal systems of quite deep, quite high temperatures. But then, of course, you need this kind of, well, persistent, deep aquifer in place. On the other side, shallow geothermal systems, like the closed systems, like ground source heat pumps with poor heat exchangers, open systems where you directly pump the groundwater, are basically possible everywhere, as long as you have an aquifer, which is kind of productive. You can also install heat collectors in very shallow depths, like 1, 2 meters, 3 meters below ground level. And you can also place them in any kind of structure. You can have thermally activated foundations, tunnel systems like here. And the best thing is you can also store energy. That you can, for example, also use an aquifer to sort of dump in the waste heat from summer, keep it there until it's winter, and you can recover most of the heat for heating your building in winter, dumping the cold down there and kind of recycling your heat every year. So now you have the resource, and of course you also need the demand, otherwise the resource is kind of useless. This is important for shallow geothermal energy because you cannot transport heat over long distances without losses. And the highest demand is obviously urban areas. So that's why most of the past and ongoing research, also in Nucci's group, is focused on how to implement shallow geothermal systems in urban areas, where we have the largest geothermal potential and also the highest demand. But urban areas are kind of tricky because there are many, many things going on in the urban subsurface. You have lots of infrastructure down there, from tunnels, subway networks, especially in London. Yeah, but also existing use of the urban groundwater. You have sewage networks, district heating pipes, and so on, and they all lose heat into the subsurface, which then leads to what we call subsurface urban heat islands. So you might be familiar with the atmospheric urban heat island. This effect that if you walk through central London on a summer day in the evening, it will be maybe warmer than if you walk through some forest area. And the same happens in the subsurface in the groundwater, so the heat accumulates in our groundwater. What we actually see then, if we measure temperatures down there, and here, 3 cities, Osaka, Berlin, and Winnipeg, so it's on all continents and all kinds of climates, it's temperature depth profiles. And what you can see here, what we would expect the profile to look like is this part down here. So we have a geothermal gradient, temperatures increasing over depth, which works nicely up to a certain point, depending on the city. And then we see this bending towards higher temperatures. And this is the subsurface urban heat island which we observe. And depending how old the city is, and of course depending on the subsurface properties, we can see that this subsurface urban heat island here goes down up to 100 meters. And this, of course, is a potential we could use, especially for heating. And at the same time, we should take care of it if we want to cool, because cooling with higher ground temperatures is obviously less efficient than with higher temperatures. Yeah, so we have to balance somehow the heating and cooling demand in cities, and we can look at the potential from different perspectives. If you want to keep it on a really large scale, what we typically do is we assess the theoretical potential. So we just take the urban area, the surface area, consider a certain depth, and we sort of calculate what amount of energy we can extract from this if we cool down or heat up the whole subsurface volume by, let's say, 5 degrees, 10 degrees, or whatever is legally possible in the city we're looking at. But it's of course not that true. It's highly exaggerated. So if you want to be a bit more specific, we can look at the technical potential, where we typically take into account, for example, the spacing of our systems. I showed you the Bohol heat exchangers, or also the groundwater wells. Obviously, you can't place them anywhere. You have to account for building footprints. They need some distance in between. So that kind of reduces your theoretical potential to a technical potential. And then, well, I mean, also because drilling is expensive, obviously, there are some economic factors to consider, which further reduces your potential. And especially in Germany, I'm not quite sure about how this is in the UK. People are kind of worried if you start digging up the ground everywhere. So there is also like a public opinion to be considered here. And it's hard to quantify this, but it is something that we should take care of. It's kind of acceptable potential. So sticking with the theoretical potential, there's a quite interesting concept which I really liked, the concept of power density. So it's just telling you energy per square meter, or if you think of the inverse, it would be the space requirement that you need to extract 1 watt of energy. So this graph actually shows a couple of cities by dots, size of population, and it plots population density and the total final energy consumption per capita per year in this city. So these solid lines you can see here, they have this unit of watt per square meter. And there are 2 lines here for geothermal, which were included in this study down here. 40 watt per square meter and 100 watt per square meter, which refers to those closed systems for heat exchangers, and to this kind of heat collectors, these very shallow systems. And you can actually see most cities are below that. So it means we could supply, so we could actually supply this for a couple of cities or kind of close going there. Yeah, but again, that's the theoretical potential. It shows we are on a good track with geothermal energy. We can supply a part of it, but probably not all of it. So then the next question is, okay, if we want to consider, let's say, the urban specific conditions and like the technical conditions of the system, one of our PhD students developed a nice workflow. So she takes into consideration all those heat sources, does then a GIS analysis, so a spatial analysis, considering where are tunnels, where are underground car parks, where there's networks, and so on. It comes up with the energetic heat flux that we as humans add to the subsurface. takes into account the energy that's already there in the subsurface, and so in the end compares this to the heating demand. So this was done for a nice city in Austria, Vienna, where we had all this data that you need for this approach. And then in the end, yeah, it's all down to this sort of what we then called or defined as the heat supply rate, or the ratio between resource and demand. Plotted this spatially, and it actually looks quite good. So we have on the left-hand side for heat exchangers, closed systems, and on the right-hand side, converted heat pumps, so the open systems. And you can see that the heat supply for both heat exchangers in most suburbs is up to 100% or even over 100%. So we could fully satisfy the heating and domestic hot water demand of those buildings by installing both heat exchangers, accounting for space limitations, the heat input into the subsurface, and the heating demand. If you look at converted heat pumps, colors are a bit darker, meaning we have lower heat supply rate, which is because those wells, if you have groundwater flow, you need lots of space per well to avoid interactions or interference between different groundwater uses. Yeah, but in the end, we could cover 85% of Vienna suburbs. And to be a bit more specific, we also sent this to the city of Vienna and make some really specific suggestions on where to go on with geothermal energy. So these are housing or planned housing areas, newly built houses, which could be easily supplied by low temperature systems. Some of them are connected to district heating, which would then be a sort of, not so good for installing geothermal systems. But there are some areas like these pink dots here, where there's no district heating, which would be perfect locations to proceed with geothermal energy. Yeah, so how we talked only about heating. Another very nice way of using the subsurface is ATES systems, so aquifer thermal energy storage. Meaning in winter, so this is an example from the Arlanda airport in Stockholm, which has a huge heating and cooling demand. And what they do, they basically take their waste heat from summer, store it in the shallow groundwater. And in winter, the whole thing works in reverse. The warm corner is pumped up, cold water is pumped down. And yeah, these systems have quite large capital costs, 5 million, but because they're so efficiently, they work so efficiently, they also have really short payback times. Yeah, temperature cold storage, quite cold, 5 degrees temperature heat storage, 15 to 20 degrees, so quite low. So there's it's not like this kind of high ATES systems where you have to take care about chemical effects. That's not the case here, and they have huge CO2 savings compared to what they used to have before. Unfortunately, in Germany, we have two-ish kind of systems like this in operation right now, but we have a huge potential for this. So this is work by another PhD student, and he created this nice map which shows you in the green colors those areas of Germany which are from the hydrogeological and also from the heating and cooling demand side really well suited for installing this kind of storage systems. And most importantly, because climate is getting warmer, we will have more cooling demand in the future. The potential will also increase for most German areas in the future. So yeah, that's definitely a way forward. And it can also save us major CO2 emissions. So we also calculated or made a life cycle assessment of those systems, taking into account the drilling of the wells, the manufacturing of the steel pipes, and everything else you need. In the end, it's more or less down to the heat pump you need, because if you're pumping, if you're pumping up the water at 15 or 20 degrees, you still need a heat pump to get to those 40, 45 degrees. You might need a heating system. So it's more or less down to energy, but energy hopefully will get more environmentally friendly in the future as well. So this is what he compared here. So we have a kind of current system with the current electricity mix in Germany in operation, and we will have even lower CO2 emissions in the future once we are based on wind, solar, and whatever. And if we compare this to natural gas, you can see that even now there's a 2/3 savings of CO2 emissions, and in the future the savings will be even higher, 96% for heating, not for cooling. Well, you might wonder, okay, why don't we do it? there's actually no real argument against it. Even economics are looking good. So this is an overview of three, not enough, but three studies that looked into the economics of those aquifer thermal energy storage systems, comparing the ATES heating costs to the gas boiler, district heating, and so on. And you can always see ATES system, ATES cooling is always much lower than the other source. And this is before the Ukraine war. So that's before the surge in gas prices. Now it would look even more extreme and more beneficial for the ATES system. But you can also see that heating costs are lower, cooling costs are much lower, which means that cooling is actually key here if we want to have economically viable systems, which is the reason why another PhD student from our group is currently looking into how can we identify not those hotspots like in Vienna for heating, but how can we identify the areas where we need cooling in urban areas. And because at least in Germany, we don't get the data is not publicly available of any kind. He looks into how can we automatically identify those chillers, other rooftops units, or cooling towers from area images, because these we get from all over the world quite quickly. So he basically developed a kind of machine learning pipeline which automatically identifies those different machines on rooftops, then uses regression analysis between the optical sort of characteristics of those systems, like how many fans are there, how big are the fans, what's the footprint of the cooling tower, and so on, because this nicely correlates with the cooling capacity. And by doing all this, we can then sort of identify the installed cooling capacity per building block. I mean, for any location that has nice aerial images available. Which I can then nicely feed into urban energy planning by having those cooling sources next to those cooling locations available. And you can play around with this quite nicely. So this is a map of the Manhattan financial district. And if you look at, that's only the cooling that's visible from rooftops. There might be more, we don't know, maybe in the sort of other systems we can't identify. But if you sum up all this, it's going to give you 1.6 gigawatt, which, if you look at it from an electric perspective, would be 1.5 nuclear power plants. And if we then sort of take the building use into consideration, apply the equivalent full load hours of cooling they would need, we get a cooling or an estimated cooling demand of this area of 1,700 gigawatt hours, which is 1.5 times the amount of a medium-sized German city, only in the Manhattan financial district. So he's currently doing this for the whole of Manhattan just to get those weird, crazy numbers. Okay, but what if we now dump all this heat into the subsurface? We might have some environmental issues, and especially in Germany, this is now quite a hot topic. Because, I mean, if we want to store all this heat, we need quite high temperatures because space is limited. We might not get away with those 20 temperatures, like for the Arlanda airport. And shallow groundwater is actually an ecosystem. So there are little bugs living down there, which keep our groundwater, which is also often drinking water, nice and clean. So these are different examples. This one is hiding there. We just didn't take the color. Oh, and I mean, they're naturally, they are not pink. They are just dyed for identification. It's easier if they are pink and not colorless. So they are living down there and they don't like high temperatures. So if we start increasing temperature, they are likely to die or just wander off to somewhere else. So this might be an issue, like the hot ongoing research topic in Germany right now. Because, I mean, as you can imagine, subsurface temperatures in city are already increased, they're already quite high. So one PhD student here from the analysis in the city of Karlsruhe looked at the groundwater temperatures, which you can see on the right-hand side, so low blue temperatures in the forest area and increased temperatures in the city area up to 17, 18 degrees. And her aim was to find out whether this ecosystem is already impacted or influenced by us, actually, or maybe there are some places where we can without doing any further harm, increase the temperature even more. This was the outcome, which was always kind of difficult to interpret. So you can see this is the forest area, the sort of presumably undisturbed area. This is the disturbed area. And there are certain areas being passed through, like in the industrial areas, we have lots of worms in our groundwater, which we don't like so much. Yeah, so their ecosystem service is not as good as, let's say, the blue ones. But still, even if it's in this high temperature areas like here, we have super large number of individuals which are found per well. What we can say is that numbers are high on either side. So all those impacts do not necessarily reduce the number of animals or the number of species we find, but we do find other species in the city area. So you can see those dark blue, available in the forest. City area is more like the other species we can find. The sort of implications for this on product quality is something we don't yet know. But for sure, there are areas here, especially to the eastern side here, where there's very few individuals around. So this is an area that we could easily use to store heat at higher temperatures, because we can't disturb any ecosystem because they're just not existing anymore. Okay, so the conclusions. Yeah, we can have major CO2 savings for Kronzos heat pumps, and especially for those aquifer permanent storage systems. Yes, they have large installation costs, but still very short payback periods, and also large global potential if you look at it. It is quite, I mean, there are methodologies to identify these sort of key locations for shallow geothermal energy use and also for storage use. Cooling is key for those storage systems, for economic and also for environmental reasons. Yeah, and we are currently working on a methodology to sort of detect them by using some clever machine learning algorithm. And last but not least, I didn't do this on my own, so I'm representing a work group here. So these are my collaborators, funding agencies, and yeah, thanks for being here. Any questions?